Hello everyone, this is Jude Lenot from Department of Physics. Here we are going to discuss about the basics of semiconductors. Before going to that, we have to know the basics in the atomic structure, that is valence band and valence shell. We know that the outermost orbit is called valence shell, and in band theory it is called as valence band. The number of electrons in the outermost orbit is called as valence electrons, and the energy required to remove the valence electron is called as ionization energy. In band theory, it is classified in terms of band gap energy. So as we see in insulators, the band gap, the distance between the valence band and the conduction band is more, so it is difficult for the valence electron to get energy and transfer to conduction band. So since the band gap is very high, it is not possible for the valence electron with the minimum energy to get transferred to the conduction band. While in semiconductor, it is somewhat less when comparing to conductors, the band gap energy, the band gap. So by giving less amount of energy, some amount of energy, we can easily transfer valence electron to the conduction band. We know that in conductors, both valence band and conduction band overlaps each other, so there is no need to give energy to the valence electron to move over to the conduction band for conduction. For example, we can take a silicon atom. In silicon atom, when the temperature rises, it means when it gives energy, what happens means the electron from the valence band get transferred to the conduction band, as you see over here, and these electrons are responsible for the conduction and called as free electrons, and the vacancy created by those free electrons in the valence band are called as holes. This represents the schematic representation of the free electrons towards the positive terminal, and this is the recombination process of free electron and the holes. The types of material are classified as conductors, semiconductor and insulator. These are the major classification, and this classified is carried out on the basis of band gap energy, and unit of conductivity is Siemens per meter. The three major semiconductor materials are silicon, germanium and gallium arsenide. So silicon has the atomic number of 14. Atomic number means the number of protons or the number of electrons. As we know, there are 4 valence electrons in silicon atom. It means that the valency of the silicon is 4. It is in the outermost orbit, and the energy which is required to remove the valence electron is called as ionization energy. The silicon atoms are evenly arranged, so we can call it as a silicon crystal. And as we know that there are 4 valence electrons for a silicon atom, and these 4 valence electrons combines with the other 4 valence electrons of another silicon atom, just forms the structure as you see now. And to attain the octet rule, there are 8 valence electrons for a silicon atom, and this forms the covalent bond. Now when the thermal energy rises, the atom vibrates, and this vibration attains energy, gives energy, and this energy is enough to break the covalent bond between the valence electron of one silicon atom to another silicon atom. So it is easily the covalent bond between the silicon atoms breaks, and due to this thermal energy, and when the electron, as a result, when the electron gets detached from its position, and it creates a vacancy called as hole. And you all know that the charge of the electron, it is negative in charge, 1.6 minus 1.6 into 10 to the power minus 19 coulomb, and this combination, generation and combination of electron hole pair is responsible for the generation of current. In semiconductors, the flow of current is due to the two types of charges. One is due to flow of electron and another one is due to holes. And this is the major difference between the conductor and a semiconductor. In conductor, the current is due to the flow of electrons, whereas in semiconductors it is classified, the flow of current is classified into flow of two types of charges. The semiconductor or further classified as intrinsic semiconductor and extrinsic semiconductor. This major classification is based on the adding impurity. It means intrinsic semiconductor refers to pure semiconductor and extrinsic semiconductor is referred as impure semiconductor. It means that the semiconductor is added with impurity atoms, and the process of adding impurities to it is called as doping. And it is further classified as p-type and n-type extrinsic semiconductors. This classification is based on the type of impurities added to this extrinsic semiconductor, and it is majority if the p-type, that is holes, or majority as impurities, it is called as p-type extrinsic semiconductors. And if it is electrons, free electrons is added as impurities in this particular material, and it is called as n-type semiconductors. And this is the major advantage of semiconductor over the conductor one. This is a reason why we are using semiconductor instead of a conductor for all the conduction process. In case of extrinsic semiconductor, it is p-type. We can consider trivalent atoms. Trivalent atom means there are 3 electrons in the outermost orbit. Examples for trivalent atoms are aluminium, boron and gallium. These 3 elements have 3 electrons in the outermost orbit. Now we can see if a trivalent atom is added to the extrinsic semiconductor, to a material. You can see here is when a trivalent atom is added, aluminium. Here we take aluminium as an example. Three trivalent atoms forms a bondage with the silicon atoms besides it, and one is vacant. It means that there is a hole is created due to the lack of a electron. Each aluminium atom has a hole due to the combination, that is vacancy, combination and rearrangement. As you know, each hole attracts the another electron, that is valence electron. Due to this transaction, each aluminum atom has an excess of hole. Due to this hole, the conduction rises, and this conduction is due to these holes, and we call it as a p-type semiconductor. The another case is n-type semiconductor. Here we can see the pentavalent atom is an example for it. The examples for pentavalent are arsenic, antimony and phosphorus. As the name refers, pentavalent, there are 5 excess, that is valence electrons are present. Now we can take phosphorus for example. When it is combined with the silicon material, the 4 atoms of the phosphorus gets combined with the silicon atoms, that is the neighboring atoms, and out of 5, 1 is the excess. 1 remains as free electron, and it is a donor atom, and each phosphorus atom has an excess of electron, and name it as a free electron. As the name refers, it is a free electron, and this is response for the conduction of current, and due to this it is a n-type extrinsic semiconductor. In n-type extrinsic semiconductor, the majority charge carriers are free electrons, and obviously minority charge carriers are holes. And in p-type, it is the majority charge carriers or holes and minority charge carriers or electrons. As we applied voltage to the p-type semiconductor, the majority charge carriers, holes, are attracted towards the negative terminal of the material, and the electrons are attracted towards the positive terminal. Since the majority charge carriers or holes over here in p-type semiconductors, the flow of current is due to the holes. Whereas in n-type extrinsic semiconductors, as we seen that the majority charge carriers are free electrons and minority or holes, the flow of electrons towards the positive terminal and holes are attracted towards the negative terminal, and the majority are electrons, and this is response for the flow of current in this type of extrinsic semiconductor. Thank you for listening. I hope this video gives you some basic ideas about semiconductors and the advantages of semiconductors over conductors.